So we've looked at how the multimeter works now, how you put your probes in and use continuity mode. So that's the start of using the multimeter. I'd say the next thing we want to learn is resistance mode. We've got a game gear here that we're going to use as a demonstration. I'm going to show you how to measure the resistance for a voltage divider on there that provides a DC bias offset for the audio output. You don't need to know how that all works, but we can show you the voltage divider in action and measure the resistance and show you the difference between testing a resistor with power on and with power off and how it makes a difference, as well as some things to watch out for when you're measuring resistance. So the principles are the same as continuity, probes in the same location. Turn your multimeter to the ohms symbol, and then we measure away. So let's just jump on the bench and take a look at this now. So here's my Fluke multimeter again. We have the probes, the black in the common and the red in the voltage. And this time we want the same mode in this case, so just turn your dial to specifically this symbol. This is the ohm symbol for resistance. Resistance is measured in ohms. The symbol we were using before is continuity, and it's in the same line. So some meters have them separate, some have them mixed. Turn the meter on. Again, most dials have an off position and simply turning turns the meter on. In this case, this is different. And we can see this is started in resistance mode. And I know that because I have a resistance symbol here, resistance gauge, and my secondary mode here, for F3 in this case, changes to continuity and now says continuity. So that's how I know I am switching between continuity and resistance on this specific meter. So if you are in resistance mode and you touch your probes together, you should get close to 0 ohms. So you can see I've got 0.12 ohms, which is less than 1 ohm. So that's basically the resistance in these leads. All wire has a resistance, all conductors have resistance. So even just a straight piece of wire, it will have some resistance. Unless you're going to go into superconductors, which the aim of superconductors is to have no resistance, you will always get resistance in a wire. But you'd expect your general test of things like dead shorts to be in the realms of 1 ohm or less. So now we're in resistance mode. Let's take out the game gear and let's have a look at what we can do here. So we have the game gear here, and there's resistors all over the board. So you can see there's plenty here, plenty here. There's also a few on the back here. And the ones we're going to test in this instance, just to show you, is R48 and R49 here. So let's just take a look at the schematic for the game gear. And these are the two resistors we're going to check, R48 and R49. Now if we check the original schematic, here's the same area. And in this case, it's R28 maybe and 27, looking at that. But the important value we're looking for here, see where it says 10K and then 10K here. So we'd expect these two resistors on this board we have here, so R48 and R49, to be about 10,000 ohms. This is just a voltage divider. So you can see this is your power connector here, where power comes in from the game gear. It goes through an inductor L3 and provides the 5 volts to the system. Then R48 goes from 5 volts through R48 and then through R49 to ground. So this is a basic voltage divider. When you have two resistances on a voltage rail and you tap the point off at a certain point between the two, in this case the middle of just two resistors, it will give you a percentage of the original voltage. In this case, because they're both the same value, 10K, we should expect half of the input voltage, which gives us 2.5 volts. So we'll get on to testing voltage after, but for now, the important thing is to just notice that we want to test these resistors. So the resistors are here, so you can see R48 and R49 there. So you can see here we have the R48, and you can see there's a little arrow pointing to it there, and R49 below it with a little arrow. So if we zoomed in nice and close, you can see that clearer. We're just going to take the meter, and what we want to do is with the probes, doesn't matter which way around they are, but touch either side of the resistor. So in this case, R48 here and R49 here. Now, if you look around, specifically on like game gears, this is quite a good quality board. In fact, a very good quality board for a game gear. But if you flip over where the old capacitors are that leak, you can see all this battery acid damage. So things like this resistor, for example, see how it's like grey, like a dull grey. So this dull grey, and you can see it flaking off, is the issue with battery acid. So it's kind of corroded and made a mess of the resistor. So when you're testing anything as well, it's important that these probes get through all this dirt and grime. So it's sometimes best just getting some IPA, isopropyl alcohol, not the beer. Don't put beer on your board. The Indian Pale Ales won't work here. If we just get some IPA and go over this to add a bit of alcohol cleaning to the board, won't do a great deal, but it will help with getting a good reading. So you can then scrape away like this and just ensure that you get some shiny metal back. And then you can be assured when you're doing a reading like this, it's going to be more accurate. So knowing how we will measure the resistance, we just need to specifically go to this one here. And what I'm going to do is I'm going to tap over R48 both ends. And as you touch, you can see the meter changes and says 4.96K. So that's 4,900 ohms. And we could see from the schematic of the one chip that was apparently 10K. Now we don't have the values of this specific board. This is a different board. This is 2-chip. So this might indicate there's a problem with this resistor, but how clean it is and what it looks like, my guess is simply that on the second revision they changed these resistors to be 4.7K. And with tolerance of most resistors being 5%, that gives us within the realm of it being a 4.7K. Because I also know that this is a voltage divider and its only job is to split the main incoming voltage in half, so long as R49 and R48 in this instance are the same value, this circuit would work. So you can see there, R49 is 4.9 and R48 is also 4.9. So even though, in this instance, the schematic was telling us that R48 and R49 should be 10K, they read as 4.9K. Now, the other thing to notice here is, see the writing on resistors? They sometimes indicate the value. So if it's the right way around like here, this could indicate 10 and then 3, the last digit being the number of zeros. This could indicate 10,000, which would mean it would be 10,000 ohms, so it should be 10K. If resistors are in a circuit, what we call in circuit, you might get different readings than out of circuit. It's not always the case, but it depends on if other things are connected to this pin or this pin that interfere with the resistance measurement. Capacitors are a lot harder to test and almost always want to be removed from circuit for an accurate reading. But resistors generally, you can just measure them in circuit and there's no problem. So before we go any further, let's now show you the difference if we connect up a power supply to the Game Gear. So I've just got a clean juice here to provide some power. And if we turn the board on, and then let's go and measure these resistors again, now the circuit is turned on and live. If you're working on an unmodded Game Gear, and you still have the 34 volt rails, be careful because there's 120 volts on this board, so don't go touching around sort of mainly this area, but generally I'd advise if you're working on the Game Gears, just watch out for the high voltage rails or mod them for a clean screen so there's no high voltage anymore. So if we go back to these two resistors now, and we measure in this case R48 again with the power on, you can see we're getting negative 2 million ohms. And the hint here is it's also showing a negative sign on resistance. Some multimeters won't do this. With this being a fluke, it'll actually figure out polarity of voltage active on the rail. And if we turn it around, it shows 20 million ohms. So this is an indicator that there's power on the board. We test the one below. You can see we're getting negative 1.9 million. So we're just getting random readings because the power's on. So if I hold the probes on there, R48, and turn the power off, you can see it drops and changes back to as it cools down, because the other indication is the warmer resistors get, they change the resistance, normally getting higher resistance. You can see as it cools down, it drops, and it will probably drop to the 4.9 once all the power's been dissipated from the board and it's cooled down. And then R49, you've got the same thing, and if we turn it on, you can see it instantly changes its reading. So it's very important, if you want to measure resistance accurately, to firstly do not power the board. And secondly, if you're suspect of what the value should be, so in this case, let's just presume we have no other knowledge, like you don't understand what this circuit's doing, but you do understand that it's apparently should be 10k. If we were unsure of this and we were measuring over here and getting a reading of 4.9k, we might suspect that somewhere on the circuit as well, because we don't know the circuit, that something's interfering with this resistor. So in that instance, what you could do, you'd make a presumption that this resistor is wrong and the value is incorrect and you need to swap it. So you'd take out your soldering iron first and you would remove the resistor from the board. So this isn't a soldering lesson, but let's just quickly remove it from the board. So a bit of fresh solder both sides, wiggle left and right at just the right speed, and then it should come off. So now we have the resistor off the circuit here, and it's just upside down at the minute. Flip it back over, you can see here. And we can now get our test lead on there, and I'll just probe over them pins, and we can read the resistance. So let's now put the probes over the resistor. And you can see when it's out of circuit, it measures correctly at 10k. So this shows how, when you're measuring something even as simple as a 10k resistor, and many of you will think that you know how to measure the resistors and you can test them correctly, you might not realize that both the power and them being in circuit affect their readings. You might go ahead and swap these and think there's something wrong with them, when in actual fact the reason these are different voltages in circuit is because the circuit isn't as simple as just these two resistors. So if we look at this being, because it's not a voltage regulated line, this is just a voltage divider line, any resistance added to these lines, say a resistor here going to ground at a later point, would affect these readings. Well, if we look around, you can see already here we have the 2.5 volt rail, which is effectively this point here is connected to the center point of these two resistors. There's now more resistors on. So there's a resistor that goes here, goes both into an operational amplifier and also back down into the ASIC of the Game Gear as well. So the internal circuitry of the circuit board plus the operational amplifier here will affect the readings of these resistors. So for truly accurate readings, you really need to do measurements out of circuit. It's a good indicator and quick tests of measuring things in circuits. And if you are, say, used to working on a Game Gear, and you know that you measure these at 4.9k, or that they measure evenly, you can be assured that they're normally okay. You don't have to be reliant on the fact that just because it doesn't measure 10k, if you have the knowledge and understand what this specific system does and measures based on a known working board, then you can be confident that testing it in circuit is okay. You don't always have to remove every component just to test it. But if you are, say, initially making your assumptions and trying to learn the board, then certainly take your time and do all the tests. Remove the power sources, make sure you've got no corrosion on the pins that you're testing with, because that'll add resistance. Make sure your meter you can trust. Don't trust the, £10 or $15 multimeters that I see everywhere that saddens me, that everybody buys, that are absolutely awful and terrible and unreliable. Just spend that bit of extra money and get a decent multimeter, because it's going to be one of the foundations of your learning. And if you can't rely on your tools or your results, then you're not going to learn anything. So just as important as proving your assumptions is disproving them. So you need to double check that you can rely on the things giving you the results, in this case our multimeter. So now it's back on the circuit. Let's just show you again that the resistance will go back to the 4.7k as it did before. So you can see there it's around the 5k mark. And you remember at the start I said there was probably an assumption that it was a 4.7k resistor. Resistors come in known and common sizes. Things like 4.7k, 5.6k, 10k, 12k. You'll get used to hearing the specific sizes of resistors. So when you measure a resistor in circuit and it seems to be close to 4.7k, your presumption isn't that it's a 5k resistor or a 4.9, you'd presume it's the common 4.7k. So we made a invalid assumption at the start that these resistors, so long as they were the same, would perform the same. So obviously I know better, but I did that as a purposeful reminder that if you have knowledge of a circuit, you may also use that knowledge to misinform yourself. So my belief was, and again, I was doing it for the sake of showing you what you might assume if you had the same knowledge, is that we know this is just a simple voltage divider. We know from the 5 volts coming in, going through here and going back to ground, should just be a simple voltage divider. So long as these two resistors are the same, the circuit would work. Now that is a correct assumption, but where we fall through is assuming that these values are 4.9k. Just because they match, that must be okay and it must be valid. However, as we saw when we removed them from the board, that wasn't the case. So you just have to be really careful when you start learning and gaining knowledge as well, that you don't make too many assumptions based on your knowledge. Always feel free to go backwards and use the basics, use the tools you have, and the most fundamental things. You want to prove that resistor's bad and you want to swap it. That's fine. Remove it off the board, but before you go and swap it, test it now it's off the board. Prove that your theory that this is a 4.9k resistor is correct, because when it's off the board, if it really was, the resistance wouldn't change. So in terms of identifying resistors, I mentioned previously that most resistors are black. You can see here on the game gear, that's completely contradictory, and these are all green. So the other thing is that resistors can be green, can be black, they can be other colors, but again, in most modern resistors now, they are black. Capacitors, the same thing I mentioned, they're usually brown. You can see here the blue, and they normally have different indicators that we'll get into. But overall, you'll get used to just looking at a circuit board, and if they didn't have things on them, you'd still be able to identify the components. So you'd be able to see straight away that these are capacitors, these are resistors, this is a capacitor, these are ICs, as we call them, integrated circuits, and you'll get familiar with just looking around boards. For resistors, notice these numbers that I mentioned earlier. These are indicators of the expected value. Again, you can get resistors with a letter and 2 numbers or different writing on that isn't always the case. But in the majority of the time, if you see 3 numbers, it normally means take the first 2 numbers, so in this case these are upside down, but 4, 7, and then the last number is how many zeros come after it. So that would be 4, 7, and then 2 zeros, so 4.7k. And again, we're going to measure in circuit, so don't absolutely rely on it, but this does say it's 472, so I'd expect 4.7k here. And you can see there we get actual 4.7k. So there's a good double indicator that not only does it say on here what you'd expect it to be, 4.7k, but the meter also reads out the same. So if I was doing these tests and I was going down these and they did ball out to the matching value, I probably would never remove these from circuit unless I was having some difficulty and really wanted to prove that. In the case of these, once you've done it once or once you have the knowledge, you'd expect 1 0 and then the number 3 to mean 1 0 and then 3 more zeros, so 1,000. So in this case, 10 and then 1,000, so 10,000. So you'd expect these values to read out at 10k. You can follow that and now you should be able to understand all these resistors. So 4, 7 and 4 zeros, what should that add up to? So 3 zeros is 1,000. So you've got an extra 0 after that. So that becomes 4, 7 and the extra 0, 470. And then 3 more zeros is 1,000. So this should be 470k based on the number. So let's go ahead and check if that's right as well. Let's probe over. And you can see here it's quite a bit off, 345. So if you were having issues with this part of the circuit, I would probably remove that resistor and confirm that it's working. So you can see even measuring resistors, the simplest of tasks that most people probably think they can do correctly, is already fraught with lots of pitfalls, things you can do wrong, assumptions you can make, the way you're testing it could be wrong. You could go over to the dirty side of the board here and just lightly press or have some poor meters and just touch over here and expect in this case 10 and 5 zeros, so 1,000,000 ohms, and you touch over here and you get potentially 1,000,000 ohms, but it's not because you've actually got the resistor right. It could be that all this battery acid is adding high resistance and measuring a higher resistance. So again, you have to make sure you have good contact to the chip itself, no dirt around it. You have to have a decent meter to read the right values. And to really be accurate, you have to remove the component from the circuit, and that's what we call out-of-circuit testing, versus when you're measuring a resistor in circuit, which is what we mean by in circuit. It means it's physically installed in the circuit that it's in. So when you hear me mentioning, oh, you're testing it in circuit, it just means in place where it is. Or you need to test it out of circuit, that means you need to remove the component and test it. One other small note before we leave it at that is resistors and most of the components change with temperature. So if this board was minus 50 degrees versus being 100 degrees, these resistors would measure a completely different value. The transistors would act differently. The capacitors would measure values differently. So temperature matters. Most components now are rated for the general temperature we live in. So, well within a range that you'd ever expect to pick up a board. The only time it's different is, say, we desolder this to measure it, and the soldering iron gets up to 300, 400 degrees, and then we instantly go and test the resistor. The value will be different. So let the resistor cool down before you want an accurate test. So there's all these things to bear in mind. But hopefully that's given you some good knowledge on how to use resistance mode, as well as some things that you need to look out for when testing. So if you remember, it's don't power the circuit, make sure there's no corrosion around the pins, get a good multimeter, and then for a truly accurate result, once you presume something's wrong, remove it from circuit, let it cool down, and test again. If you follow all these steps, you can be assured that when you're measuring a resistor, you can be confident that the value you see on this screen is accurate. If we were to measure this resistor and think it was a 10K resistor and it's measuring 4.9, we could remove this resistor, reinstall another 10K resistor without testing the other one, measure again and go, oh, it's down to 4.7K. It must be something wrong with the circuit board or something else going on. And you've simply missed the fact that you didn't prove your assumption that that resistor was 4.7K, because when you removed it from the board, you didn't double check and do that extra step again. So all these things are important. Every little step and every little detail is very important to relying on your results. If you can't rely on your results, don't go any further. You need to be assured as you start to build your knowledge up that you know absolutely your results and your assumptions are sound, and that you're confident in when something's measured, is it the accurate result? You could go down a massive rabbit hole trying to find a problem that doesn't exist just because you didn't measure the simplest component in the first place. So I guess next up the obvious step would be to put some voltage in here and to test the circuit we just measured. So I'll show you next how to use voltage on your multimeter, and we'll see how this circuit actually works.